In the last lecture, we started to talk about electrophilic aromatic substitution and the idea that if we can take an electrophile or make a strong enough electrophile that will add to the double bonds of a benzene ring, that what will happen is that we'll in essence add the electrophile to one of the carbons of the double bond. We will end up forming then an allylic carbocation intermediate, and that allylic carbocation intermediate then will have a series of resonance structures that in essence will make it stable, but instead of adding a nucleophile to each one of these carbocations and doing what we would have looked at in the last chapter as being 1,2, 1,4, and 1,6 addition, that the ring is going to want to reform the aromatic system so that it can go back to its super stable aromatic benzene ring. And the way that that's done is not by electrophilic addition, but by electrophilic aromatic substitution, where we simply lose the hydrogen that is attached to the carbon where I added my electrophile, and then I reform the ring. And in essence, what I've done is I've substituted the electrophile for a hydrogen on the benzene ring. That's electrophilic aromatic substitution. And then we looked at three ways that we can generate electrophiles that will be strong enough to add to a benzene ring. The first was that if we mix nitric and sulfuric acids together, we make the NO2 plus electrophile, so that if I took a benzene ring and I added those reagents to it, I would put a nitro group on the ring, and this would be a way to nitrate a benzene ring. If I mix SO3 and sulfuric acid, I can then replace or substitute a hydrogen on the benzene ring for a sulfonic acid group, and so I can sulfonate the ring. And of course, then I can turn this OH into a Cl and make my begin to make my tosyl chloride type compounds. And then the final thing is that halogens like Br2 or Cl2 will not add to a benzene ring by itself, but if we add a catalyst such as FeBr3 or AlBr3 or FeCl3 or AlCl3, these catalysts, that what will happen is that the bromine molecule will actually react with, let's say, FeBr3, and we will end up forming a very potent Br+, which is now going to be our electrophile, and then we would form FeBr4 minus this Br+ then, or Cl+, if we did this reaction with iron trichloride, we would end up with the Br+ adding to the ring, and so we could actually halogenate rings and substitute a hydrogen for that halogen, or that hydrogen with that halogen. So there's a few more reactions that we can do, electrophilic aromatic substitution reactions, and of course it's nice to be able to nitrate or sulfonate or halogenate a ring. But remember, the real important reactions are the ones where we form carbon-carbon bonds. And so if we could form a C+, then we could add that C+ to the benzene ring. Well, Friedel-Crafts, and Crafts is not like the cheese. That's one of my pet peeves, that people will spell this like the faux cheese as opposed to the guy's actual name. But Friedel-Crafts actually came up independently with ways to add alkyl groups to benzene rings. And they did this in the late 1800s. They did this independently. James Crafts, I believe, was either an American or an English chemist, and Friedel was a German chemist. And what they found was if they took an alkyl halide and they reacted it with aluminum trichloride, and let's say, for instance, that I take tertiary butyl chloride and I was to add to that aluminum trichloride, that the same reaction that occurred with the aluminum trichloride and the Cl2 that we just saw would happen with the alkyl chloride. So here's my AlCl3. So in other words, the chloride, carbon chloride bond would break and the Cl- would go to the aluminum. That would then leave me here a tertiary carbocation and an AlCl4 minus counterion. Well, this is the traditional way that Friedel-Crafts were able to generate carbocations. And then, of course, once they formed this carbocation, it would add to the benzene ring. So, for instance, if I did this reaction where I took tertiary butyl chloride, reacted it with aluminum trichloride with benzene, I would have ended up forming tertiary butyl benzene. I would have replaced a hydrogen with that tertiary carbocation. Well, Friedel-Crafts, this was their method, and this is traditionally what's been called the Friedel-Crafts alkylation reaction. So in other words, when we add an alkyl group to a molecule, that's called alkylation. They basically found that this reaction works well with tertiaries, and it could also work with secondaries. So for instance, I could take isopropyl chloride, react that with aluminum trichloride and benzene, and that would then generate a tertiary butyl carbocation, or not a tertiary butyl, but an isopropyl carbocation, which would then add to the benzene ring to give us isopropyl benzene. So this reaction works pretty well with tertiary and secondary alkyl halides. But the reaction is subject to carbocation rearrangements, and this is primarily with primary alkyl halides. So let me go back here and show you what happens in this reaction. So you can actually do the reaction of methyl chloride, ethyl chloride. You can use these to react with aluminum trichloride and benzene and the benzene ring. So you can take benzene and react it with ethyl, methyl chloride, and aluminum trichloride, and you will make toluene, or you will make ethyl benzene. Now, for those of you saying, but wait, how do you get, if methyl chloride reacts with aluminum trichloride, that must mean that you formed this, and we're not allowed to draw this. Or down here with the ethyl chloride, that must mean that you formed this, and that's a primary carbocation, and even worse, a methyl carbocation. You don't let us draw these. How do these even form to be able to react with a benzene ring? And you're correct. These actually don't form in these reactions. Here's what happens. When you take the methyl chloride and you react it with aluminum trichloride, what happens is that the chloride becomes associated with the aluminum. And so what you end up with is sort of a kind of a transition state here where the chloride isn't completely removed from the methyl group. Instead, the chloride is pulled away from the methyl group to the point where enough delta positive charge builds up that this then becomes electrophilic enough to add to the benzene ring. So at some point when you get enough of this delta plus charge, then this will go ahead and become a strong enough electrophile to then add into the benzene ring. So we never quite form a methyl carbocation, or for that sake, we don't even form an ethyl carbocation. We just simply, in the case of the ethyl group, we stretch the carbon-chlorine bond to the point where, again, we build up enough delta plus charge here that it can now become an electrophile and add to the benzene ring. But what happens when we take and we try and do this reaction with N-propyl chloride? So if I take this 1-chloropropane or N-propyl chloride, react it with aluminum trichloride and benzene, is that the aluminum will still kind of associate with the chlorine and stretch the bond. But in this case, because this is now a propyl group, what can happen is that I can get a carbocation rearrangement. And so if I form that kind of transition state or high energy species where the chlorine is being pulled away, what will happen is we'll get a 1,2 hydride shift. And that 1,2 hydride shift then will end up forming a secondary carbocation and not the primary one that is our goal here if we wanted to add a propyl group to the benzene ring. So when you try and react 1-chloropropane with benzene, you end up with isopropyl benzene, not 1-chloro, or not N-propyl benzene. Okay, so let me go here to a slide. Okay, so just rewriting that reaction, what would happen is if I did this reaction, I would end up forming isopropyl benzene, not propyl benzene. And this is a universal problem with primary alkyl halides. We can't react primary alkyl halides with aluminum trichloride and benzene to form straight-chained alkyl benzenes. We're always going to get a rearrangement reaction to occur when we try and add straight-chained alkyl benzenes, straight-chained alkyl halides to benzene. We're always going to get a rearrangement, and we're always going to form the secondary alkyl groups. And we'll talk about a way to overcome that in a couple of minutes. So Friedel-Crafts alkylation is subject to carbocation rearrangements, but it is possible to use methyl and ethyl to form ethylbenzene and methylbenzene, which we know is toluene. So we'll talk about how to overcome the straight-chained alkyl halide addition and get a straight chain on this end. We'll talk about that in a couple of minutes. Okay, so if you were going to do a Friedel-Crafts alkylation, let's say that I wanted to form, let's say we wanted to form secondary butylbenzene. How would I do that? Well, I would take secondary butyl chloride and react it with aluminum trichloride, and that would give me then the secondary butyl carbocation, which is stable, and then that's what would add into, that would then attack, what would then happen is we would have this double bond, then add that electrophile. So we would end up with our secondary and our hydrogen there, our carbocation here. We could draw all of the possible resonance structures, but I'm just going to cut to the chase and say, okay, after the carbon adds here, I'm going to lose an H+, and I'm going to reform my benzene ring now with the secondary butyl group attached. Now, Friedel-Crafts also came up with another variation of this reaction, and that is to do what's called Friedel-Crafts acylation. And in this case, what they did was they took a carboxylic acid chloride and they reacted it with aluminum trichloride. And the same thing happens. You have the aluminum remove the Cl minus, or the Cl minus goes with the aluminum, and then we end up putting a carbocation on the carbonyl carbon. We end up with that plus charge. Now this is called an acyl. It's called an acylinium ion. And you might say, well, is that stable? Well, sure it is. Because if we have the plus charge on the carbonyl, I can draw a resonance structure by taking one of these lone pairs, moving it here, and then that gives me this other resonance structure to stabilize the acylinium ion. Now, what happens is that it's the carbon that is the electrophile, and that's what's going to add to the benzene ring. So in the end, if I do Friedel-Crafts acylation, I'm going to attach then a carbonyl group and make what is called a phenyl ketone. And this benzene ring, when it's a substituent, is called a phenyl group. It's like a cyclohexane ring as a substituent. It's called a cyclohexyl group. Benzene is called phenyl. So this is called a phenyl ketone because it's a ketone with the phenyl group on it. So we can do Friedel-Crafts acylation. The only thing is we have to be able to make our carboxylic acid chloride, but we already know how to do that, because in order to do that, we just take any carboxylic acid, react it with thionyl chloride, then that makes our acid chloride. So Friedel and Crafts came up with ways to alkylate and acylate benzene rings. Those are important reactions as we form carbon-carbon bonds. They win the Nobel Prize for that. Now, we actually know a lot of other ways to add alkyl groups to benzene rings. And you might say, well, I don't know any, but you do, Crafts. For instance, here's a reaction of benzene H plus and 1-methylpropene. I would get tertiary butyl benzene as the final product. Now, if you're sitting there saying, hey, I know how you do that, stop the tape, write the mechanism. If you don't, how do I get this product? Well, H plus is an electrophile. It can't add to benzene because benzene is too stable to react with H plus on its own. This alkene is a nucleophile, so it's not going to react directly with the benzene. But the H plus will react with this propene. So if I have carbons A and B, where will the H plus add in this molecule? If you said the H plus will add to carbon B, you're right, because that's Markovnikov addition. That then adds H plus to the carbon with the most hydrogens, which is B, to form the more stable carbocation, which is a tertiary carbocation A. What happens? I now have a tertiary butyl carbocation. It now adds to the benzene ring, and I make tertiary butyl benzene. So how many other ways do we know how to make carbocations that would then add to benzene rings? Well, H plus and an alkene. How about tertiary butyl alcohol and an H plus and a benzene? What would that make? Well, we would protonate the OH group, right, to form our oxonium ion. And then we would break the carbon-bromine or carbon-oxygen bond. So we would lose H2O, and we would form then a tertiary butyl carbocation, which would do what? Which would add to the benzene ring. So there's another way to make terse-butylbenzene. So any way that we've learned so far to make a carbocation, if you did that reaction in the presence of benzene, you would do electrophilic aromatic substitution and make that alkyl benzene, right? So the Friedel-Crafts method, this is the traditional Friedel-Crafts method, but after a lot more reactions were discovered, there were other options besides doing Friedel-Crafts alkylation. And these are just two of them. Acid alkene benzene or acid alcohol benzene. Of course, you got to be able to form the carbocation, right? Once you form the carbocation, then that will react with the benzene ring. So Friedel-Crafts, we can do alkylation, we can do acylation. Now, why did I show you the acylation? Because remember, we have a problem that if we tried to make propylbenzene, we can't do it by reacting 1-chloropropane and aluminum trichloride, right? We can't do that because that would undergo a carbocation rearrangement, and I would end up with a secondary carbocation. I would end up with isopropyl benzene. So there has to be a workaround to add a straight chained alkyl group to a benzene ring, and here's what it is. The first step is to take the benzene ring and convert it to a phenyl ketone. We know how to do that. Take your alkyl halide, or take your acid chloride, aluminum trichloride, and make the phenyl ketone. Then what would be really nice is if we could reduce this carbonyl group down to a CH2 group in one step. And you may say, didn't we learn how to do that before? No. We learned how to get rid of, let's say, an OH group by, I don't know, taking the OH group and converting it to a tosyl chloride and reacting it with hydride, or making this an alcohol and putting a double bond and then using hydrogenation on it. But here's a couple of one-step methods to reduce a ketone all the way down to an alkane in one step. The first is what's called Clemmensen reduction. And in Clemmensen reduction, what we do is we react a phenyl ketone with a zinc mercury amalgam. So what this is this is zinc metal mixed with mercury metal to form a bimolecular metallic species that's called an amalgam. Anything mixed with mercury is called an amalgam. My teeth probably have mercury fillings in them, and so that would be an example of an amalgam. They don't do that anymore. They use ceramics and everything else. But the zinc mercury amalgam with HCl and heat. We're not going to talk about the mechanism of this, but what this does is it reduces this carbonyl down to a CH2 group. So if I wanted to make propylbenzene, I would come over here and I would start with benzene, and I would react this with, not my R group, now I want to be specific, so I want to react this with propyl carboxylic acid. I'm going to react not the carboxylic acid, right? I'm going to react the carboxylic acid chloride with benzene and aluminum trichloride. That's going to form the phenyl ketone now with the CH2CH3 group on this side, and then I would use my Clemmensen reagents to reduce this carbonyl down to the straight chain propane group. So this is a workaround for adding straight chained alkyl groups to the benzene ring, because Friedel-Crafts just doesn't do it without undergoing that 1,2 hydride shift. There's another reduction that you can do of a phenyl ketone, and that's what's called Wolff-Kishner reduction. And Wolff-Kishner reduction involves reacting the phenyl ketone with a molecule called hydrazine, and then followed by KOH and heat. So if I did that same reaction that I just did on the previous slide, I have my reaction of the propyl acid chloride with aluminum trichloride to make this phenyl ketone, and I did Wolff-Kishner on it, I would say, okay, I'm going to react this with N2H4, KOH, and heat. That's Wolff-Kishner reduction. That's going to reduce that carbonyl group down to my propyl benzene. Okay, so Wolff-Kishner is the second way to do this. We'll talk about how we form hydrazines later on in the semester, and we probably won't talk about the KOH and heat step, but this is Wolff-Kishner. Now you need to know the reagents for Wolff-Kishner, as well as that those reagents are called Wolff-Kishner. Same thing's true for Clemenson. You'll need to know what the reagent is, as well as the fact that that's called the Clemenson reduction. But the whole point of this is a way to reduce phenyl ketones down to alkyl groups. And this is a perfect way to make straight chained alkyl benzenes, is to combine these two reactions together. Okay. Now, so we have our reactions of benzene. I can take benzene and react it with a whole bunch of different electrophiles and make substituted benzenes. Nitrobenzene, bromobenzene, chlorobenzene, and propyl, etc. But what I really need to be able to do is not react benzene, because benzene's boring. What I really need to know is, if I had toluene and I was to react toluene with HNO3 and H2SO4, what product am I going to get? Well, I could add, if I looked at this, I'd say, oh, well, I'm making an NO2 plus. And then you'd say, well, where's the NO2 plus going to add? Is it going to add ortho to the methyl group? Is it going to add meta to the methyl group? Or is it going to react para to the methyl group? So am I going to form orthonitrotoluene, metanitrotoluene, or paranitrotoluene? Or am I going to form a mixture of all those? So what's the major product of that reaction? Well, we'll come back to that in a minute. Instead, what I want to first talk about is what effect does adding a group to the benzene have on electrophilic aromatic substitution. So in other words, when a monosubstituted benzene is reacted in an electrophilic aromatic substitution, what effect does a substituent have? Well, it could have two effects. It could make the reaction occur faster or slower than benzene. It could speed up that electrophilic aromatic substitution. It could slow it down. So that's the first thing we need to talk about, is does the reaction go faster or slower? Then the second thing that we need to know is we need to know what the major product is. So this group is what we're going to call a director. And it's going to tell the electrophile where to go. It's going to say, go to the ortho position, go to the meta position, go to the para position. And so we need to talk about what groups direct to what positions. And so that's going to get kind of at our regioselectivity from last semester, regioselectivity of the reaction. Okay? And groups are going to fall into two classifications that some of you have already been introduced to in lab, the idea of electron withdrawing groups and electron donating groups. So we'll talk a little bit about what makes each. So let's deal with number one first. What does that substituent do to the benzene ring reactivity? Well, in order for us to think about this, what we need to think about is the fact that we've got a benzene ring, and the benzene ring is a nucleophile. I'm going to put a Y group here, just a generic Y group. So this is a nucleophile, and it's going to react with our electrophile. How can I make the ring react faster with the electrophile? If you said make the ring a better nucleophile, you're right, but how do I make this a better nucleophile? Let me restate the question. How do you make this ring more electron rich? Let's put a group on here that pushes electron density into the ring. And that'll make the ring more electron rich, more nucleophilic. It'll react faster with the electrophile. Does that sound reasonable? Now we just have to talk about how the groups do that, but in theory that's what we do. Well, a group that pushes electron density into the ring is called an electron donating group. Well, just the opposite can occur. What if I take my benzene ring and I'm reacting it with my electrophile and I attach a group that sucks electron density out of the ring and makes the ring less electron rich? What will happen to this reaction? Well, if I've got a weaker nucleophile, this is going to slow down the reaction. So the reaction is going to go slower. Up here, by pushing electron density in, the reaction goes faster. By pulling electron density out of the ring by my Y group, the reaction goes slower. These are called electron withdrawing groups. And that's what you kind of talked about in lab with the Diels-Alder reactions, because what's actually known is that when you attach electron withdrawing groups to alkenes, you get faster Diels-Alders. But now we need to define exactly what do we mean by electron donating and what we mean by electron withdrawing. Okay, so that's the basics. Well, here's a list, an experimental list of groups that either cause the benzene ring to react faster or slower. Ultimately, you're going to have to memorize this list, and you're going to have to know the groups from number 1 to number 10. But let's just start with the experimental results. So here's benzene. Benzene is my baseline. So anything that reacts faster than benzene is going to have an electron donating group on it. Anything, so this would be our list of electron donating groups here in blue. And anything that reacts slower than benzene is going to have what we call an electron withdrawing groups. And so here's our examples of electron donating groups and electron withdrawing groups. Okay. And some of these, again, you may have talked about in lab. The idea that if you have a carbonyl group attached to the ring, that's electron withdrawing. Carbon triple bonds or CN triple bonds also reduce, they're also electron withdrawing, so are halogens. Now we'll talk about why each one of these is electron donating or withdrawing here over the course of the next couple of minutes. But this is experimentally what we find. The most donating groups are groups where you have a nitrogen attached to the ring with a lone pair. Second most donating are groups that have an oxygen with lone pairs attached to the ring. Third most, I keep using this activating term, I'll come back to it in a moment. The third electron donating group, another benzene ring. And then alkyl groups will donate electron density to the ring. Electron withdrawing halogens withdraw a little bit of electron density, carbonyls a little bit more, C triple bond N a little bit more, NO2, and remember NO2 looks like this, withdraws even more. And if I put a nitrogen that's got 4 alkyl groups attached to it so that it has a plus charge, an ammonium salt, that it withdraws the most electron density. So this is what we find experimentally. Now why? Well, so we can push electron density in or we can pull it out. Groups that push electron density into the ring are called activating groups. So the electron donating groups, we say activate the ring. Electron withdrawing groups, they deactivate the ring. So we use activate and deactivate to basically say this ring will react faster in electrophilic aromatic substitution or slower in electrophilic aromatic substitution. Okay, great. So now I'm going to use those terms activating and deactivating to indicate electron donating, faster reactions, electron withdrawing, slower reactions. But now we need to deal with the issue here. How? Well, before we get to the exact how, we need to introduce 2 other terms. Groups can donate or withdraw electron density by 2 mechanisms. One is called an inductive mechanism, and the other is by resonance. Now, inductive means that you push or withdraw electron density through a sigma bond. This is an electronegative effect. For instance, a halogen like bromine withdraws electron density from the ring. This is an electron withdrawing group. Why? Well, because when you have a carbon-bromine bond, you've got a polar covalent bond. The bromine becomes delta minus, and then this carbon becomes slightly positive. So what have I done? I've withdrawn electron density from the ring through a sigma bond, basically through an electronegativity effect. How'd the bromine become delta minus? Because it sucked some of the electron density out of the ring. Let's say I've got an alkyl group. Going back to the chart, alkyl groups are activating. They push electron density into the ring and cause it to react faster. How do they do that? Well, carbon-hydrogen bond. Slightly polar covalent, the hydrogens are delta plus. That makes the carbon delta minus. What does it do? It now has the ability to push the electron density into the ring through the sigma bond. So both of these are inductive effects. This is your electron donation, an electron donating group through induction. This is electron withdrawing through induction. Okay. Now in general, inductive effects are weak. And if we go back to this chart, here's our benzene. This is our baseline. Notice that the group that reacts just slightly faster than benzene uses induction. to push electron density, to donate electron density to the ring. The group that's just below benzene has a halogen. It withdraws electron density by induction. So inductive effects are pretty weak. That means that when we get to the other groups that are farther away from benzene, either much faster or much slower, that the second mechanism is going to come into play. And the second mechanism is what's called resonance. So can we draw resonance structures that in essence push or withdraw electron density into the ring because I can draw those different resonance structures? These are going to be much stronger approaches. So let's say, for instance, that I attach an atom that has a lone pair on it to the ring. This would be, maybe I have an oxygen with 2 lone pairs, maybe I have a nitrogen with 1 lone pair. Well, if I have that atom that has the lone pairs, here's a series of resonance structures that I can draw. I could take this pair of electrons and move it here to form this double bond, but then at the same time I've got to break this double bond and put the negative charge, the pair of electrons, on this carbon. Then I could take this pair of electrons here, move it to this double bond, move it, form a double bond there, break that bond, and then put the negative charge there, bring this here, and then bring the negative charge out to that carbon. So here's what I've done. I've drawn 3 resonance structures by taking this lone pair and in essence pushing density into the ring. Because if I come down here, what I see is that the resonance hybrid of these 3 structures has a ring that has some delta minus charge. So in other words, this ring is going to be more nucleophilic and is going to be activated. So any atom that's attached that has a lone pair on it, like nitrogen and oxygen, by drawing these 3 resonance structures, I've now pushed electron density into that ring. So if we go back to our chart, we can see that the resonance effect plays a role with nitrogen and with oxygen. And these are the 2 most activated groups that I can have. Therefore, resonance must be a very powerful tool to push electron density into the ring. Now, what about the other benzene ring? Well, if I have 2 benzene rings attached, I can think about drawing now different resonance structures here by maybe taking this pair of electrons, using it to form this double bond, and then at the same time breaking this bond and putting a negative charge here, bringing that pair of electrons there, the negative charge out to that carbon, and then bringing the negative charge here and that pair of electrons out to this one. So what I've done by being able to draw these 3 resonance structures is that I have increased the electron density in the ring. Okay, I've caused the other benzene ring to be, kind of a little bit less electrophilic, but I've increased the electron density in this ring, and therefore I've made it slightly more nucleophilic. And so just above the inductive effect of alkyl groups is the benzene ring. So that's how we explain why this is an activating group. So what we see is that resonance, activation by resonance structures, is much more powerful than the way the alkyl group activates by induction. Okay, so that's all I'm doing, is just drawing different resonance structures to show how I can push electron density into that ring. All right. What about deactivating? What about pulling electron density out? Halogens pull the electron density out by induction. How does a carbonyl or a C triple bond N or an N double bond O, how do these groups right here withdraw electron density from the ring? And I'll give you sort of the first part, and they do it by resonance. I'm also going to say that, what's the common feature of these three structures? They have an X atom that's multiply bonded to a Y atom. C double bond O, C triple bond N, N double bond O. And if I looked at the charges, remember the carbonyl has a delta plus, delta minus charge. The carbon would have a delta minus, delta plus charge here because carbons, no, this would be delta plus, this would be delta minus. Nitrogen's more electronegative than carbon. Down here I got a full-blown plus charge and a full-blown minus charge, or a full-blown plus charge and actually remember that the nitro group, the real structure of the nitro group is like this. Delta minus, and plus 1. So I got a plus delta minus charge on that. So here's what I'm going to use as my generic structure for all three of these. An X with a delta plus and a Y with a delta minus, because that resembles these three structures. Okay, so now here's my X multiply bonded to Y. My X has a delta plus charge, my Y has a delta minus charge. Well, looking at these two, first you might say, this delta plus charge, doesn't that suck some electron density out of the ring? Okay, it does, but not a whole lot. Here's what really pulls the electron density out of the ring. Because I could take this pair of electrons and move here to form a double bond, and then give this pair of electrons to the Y group, so that I would have a plus charge in the ring and a Y minus group here, and a Y minus charge there. And that's okay because Y was less electronegative than carbon, so it can take a negative charge. So then, got an allylic carbocation here, and I can move the plus charge around the ring. Which means in the end, by drawing these three resonance structures, what have I done to the ring? I've made it delta plus. I've sucked electron density out of it, and I have deactivated it. So all three of those groups deactivate by being able to draw these three resonance structures. And so they're more powerful. If I go again back to my chart, carbonyl does this a little bit, CN even more, and the NO2 with the full-blown positive charge here, that's really deactivating my ring. So these three guys deactivate by resonance. Okay, would I ask you to draw these resonance structures? Maybe on a take-home quiz. Well, maybe on an exam too. But maybe on the third exam, not the second one. Okay, so here's my three resonance structures for the deactivating, for a generic structure of a deactivating group. Okay, as we've seen, alkyl groups activate by pushing, by induction, and halogens deactivate by induction withdrawal. Last one on the chart's N+, and this will be the end, because they said don't go above an hour. Here's my ammonium. It is dead last on the chart. I think I got another chart here. It is dead last. Why? Well, when you have a full-blown positive charge here, that's going to withdraw electron density how? By induction. Now you could say, really? That's what makes an ammonium dead last on the chart? I don't think so. I would probably say, okay, yeah, it deactivates the ring by induction, but I might go a step further. And I might say this. I get a positively charged ammonium with a benzene ring, and I'm trying to add an E plus to that. What's the big problem here that's going to really slow down this reaction? I'm trying to react two positively charged things. That's not really going to be likely. So it's going to be exceptionally difficult to add an electrophile to an already positive ammonium on a ring. So I don't know that it's so much the inductive withdrawal that's removing electron density from the ring and making it deactivating. I think it's just the issue that plus doesn't play well with plus. So that's the primary reason why we've really deactivated that ring and made it dead last. Okay. So here's the experimental list of activating and deactivating groups. Again, benzene is our baseline. These three groups activate by resonance. The alkyl group activates by induction. The halogen deactivates by induction. And these three X multiply bonded to Y groups deactivate by resonance. And the NR3 group, the ammonium group, yeah, it probably deactivates it does deactivate by induction, but it mostly deactivates because it's got a positive charge and it's not going to react with a positively charged electrophile. Okay? So, we have just answered question numero 1 here. What effect can the group that's attached to the benzene ring have? It can make the reaction occur faster or slower. Here's how. What we need to deal with in the next lecture is great. So if I have a substituted benzene ring and I'm going to react it with the electrophile, is the electrophile going to go ortho, meta, or para to that initial group? Am I only going to get one of these? Am I going to get a mixture of these? Am I going to get some random mess of those? Well, that's what we have to deal with in the next lecture on this.